right? So you take the norm of that and then divide by the norm of un. What will you get? Well, just take norm of tun. Just write norm of that.
Okay.
And on the right, what do you get?
That.
Right, but n squared is a number. You could pull it out. Okay, just write it. N squared times the norm of Vn. Okay. And now divide by the norm of Vn. What do you get?
And supreme.
Well, it's not equal to
It equals the supremum of that. Right.
supremum of n squared over all n. So what is it?
So infinite. It's unbounded.
Infinite. It's unbounded operator, right? So there is no infinite. So differential operators are all unbounded operators. That's all I wanted to show you. That you talk about bounded operators, but differential operators are unbounded. So if you want to solve differential equations, you got to develop a theory for unbounded operators. Okay? Well, let's say you have, instead of this t, well, say you have an equation that looks like this. T plus 1 is equal, t plus 1 acting on u is equal to f. Just write it over there.
It's t plus 1 equals.
T plus 1 plus 1. No, act this whole. Put the t plus 1 in brackets.
Sorry, what?
T plus 1 is a whole thing acting on function
Okay.
u.
So t
On u equals f. Okay.
equals
F.
Yeah.
So now try to find u from this. Well, it's an inverse of that operator, right? So just write u is equal to t plus 1 inverse. T plus 1 inverse. Okay, so what's the norm of the operator t plus 1 inverse?
That'd be 0 or 1. One of those two.
Well, you already
Yeah.
have, well, just take t plus 1 inverse and try to compute its norm.
Okay.
You have to take un, apply this operator to un, and see what you get. Just write t plus 1 inverse acting on un is equal to what?
Okay.
Acting on un, just apply to un. What is it equal to? Well, t on un is n squared, right? So all you have to do is to replace t by n squared.
So it's,
So what is it?
yeah, so then it's
Just write what it is, equal to.
un for n squared plus 1.
Right, okay, and then take the norm of that, like you did over there.
So,
Take the norm of the whole thing and divide by the norm of un.
okay. So that is it's divided by un plus 1, and it's the supremum of that.
Yeah, just
So-
write supremum of that, what is it?
That is 1/2.
Is that clear? Which is a bounded operator. Is that clear to you?
Yeah.
Okay. You may continue, I just wanted to give an
Okay.
example.
All right, yeah, so I guess, should I start going into that? So I guess I'll go ahead and define the, like, resolvent and kind of the basic stuff for, like, what a spectrum is, which is kind of like a infinite dimensional generalization of eigenvalues and eigenfunctions. So we have, the resolvent set, rho of t. And what we define is that all elements in rho of t, or an element is in rho of t, if, or wait, let's pass. Write that down. Okay. So for all complex numbers, it is in rho of t if the resolvent set minus T exists.
It's not the resultant set, it's the resultant.
Yes, that's
it's the
the
operator.
result, that is, yeah. So so for all complex numbers, it's in the resolvent set if the resolvent exists.
So if that operator is invertible, C
Yes.
minus T.
Yeah. So one of the implications, or one of the things this is that the resolvent set itself is always open. So then we can then go ahead and define the spectrum to be the complement of the resultant set, which, because that's always open, this has to be this is compact and is also non-empty.
Why is it compact? It's closed, but not.
Yes.
Why is it compact?
They went over that in the book. I did not write down the specific.
Well, it depends on the operator T. What did you assume about
It's
operator?
bounded operator.
Okay, that is
Yeah.
bounded.
So for a bounded operader, then it's compact. For an
For
unbounded,
differential operator, it
Yeah,
would
it's
be
not.
not compact.
yes, because that is infinite. As we showed it has an infinite number of eigenvalues.
It's not the infinite number, it's unbounded. That's
Unbounded.
what.
Right. And so, of course, because this is the opposite of that, or since this is the complement of that, and this is the prerequisite for being in a row, or being in the resolvent set, then here we have to have that verse is undefined, so that we have to have that IIT is equal to 0, making this so. And from that, you can kind of see how it's.
Well, why is it equal to 0?
I guess it could equal infinity as well.
No, it isn't equal to anything. It just means that this operator is not invertible.
Okay.
This is an operator, it's not equal to 0.
Right.
Because if it's equal to 0, then the operator T is just C times identity. That's
Okay. Yeah, sorry, I was trying to make, I think I was trying to connect it with the, kind of definition for a finite eigenvector of a matrix.
well, look at the matrix. Okay, if the
Yeah.
matrix is not invertible, this means that it's equal to 0. It means that it has a 0 eigenvalue,
Yeah.
maybe just 1.
Yeah. Alright. So yeah, so that is not invertible. Like I said, with the spectrum, we kind of went over, I guess, an example already with the differential operator there. But I guess another example would be kind of with the so I guess why this is useful is solving that equation there, but also something larger like the Schrödinger equation, where H is differential operator. We can then write the solution in terms. We can then write the solution. This was specific.
What is that
Yes.
in the exponential?
E. So basically the eigen
And then
T.
what is T?
This was, I did not solve this by hand. This was just found on an example I found off the internet.
Well,
So
that's not this equation. This equation is called stationary equation.
Okay.
This, what you wrote, is a solution of a time-dependent,
Okay.
non-stationary
So-
equation.
No time.
No. Well, just write different equation. Just leave the time here. Just write the equation. Instead of E in that equation, write I times d by dt.
Oh, for here?
Here, yeah.
Okay.
I d by dt. And then
Okay.
here you would have I also.
Here?
Yeah.
Okay.
Then, well, and then what is phi k?
Where phi k is the eigenfunctions of the operator H.
Okay, write the equation for that. H phi k is equal to what? Okay.
So, yeah, and so that lets us, get a solution in terms of the eigenfunctions, which is why this is useful and why functional analysis in general, I guess, is especially relevant for PDEs, because it does let us manipulate solution, or it does let us manipulate operators like that. All right, admittedly, that's pretty much all I have. Like I said, most of the appendix where it reviewed functional analysis was, really lots of in-depth proofs and such, which I don't think we were. The goal of the seminar is not really to go over that. So yeah.
Good. So you're almost at 40 minutes. Yeah, that's not the shortest lecture.